Hello and welcome! In this basic tutorial, you will learn how to handle robots in iiQWorks.Sim. The goal is to help you get familiar with the user interface and understand the first navigation steps. In this example, we are using iiQWorks.Sim Basic. I will guide you through the initial views and show you how to move around the environment so you feel comfortable working with the software. At the moment, you are in the Home tab. In this tab, the eCatalog view is active. The eCatalog is your main entry point to access robots, components, and other simulation objects. You can switch between different views depending on what you want to work on. At the bottom of the screen, you can see several tabs that represent different views available in iiQWorks.Sim. These tabs include the eCatalog, the cell graph, and the devices view. Each of these views focuses on a different aspect of your virtual cell. For now, we will not go into detail about these views. You will see how they affect your workflow at a later stage of the tutorial. Let us return to the eCatalog. The eCatalog contains a structured library of objects that you can use to build your virtual robot cell. When you click on the small arrow next to the library entry, you can expand the iiQWorks.Sim library. This is where you will find the available KUKA robots. All KUKA robots in the tool are organized by payload classes. This makes it easier for you to select a robot that matches your application requirements. For example, you can open the High Payload category and select a Quantech robot. This category contains robots designed for handling heavy loads. Even though you have selected the robot, nothing is visible yet in the workspace. This is related to the current layout of the user interface. To solve this, you can either collapse some of the library collections or increase the visible workspace area so the robot models become visible. In this case, you simply drag the library window slightly to the side to resize it. Now the robots are visible, and you can clearly see the selected models in the workspace. You can scroll up and down in the eCatalog to browse through the list of robots, or you can use the search bar to quickly find a specific robot model. In this example, I select the first robot that appears in the list, which is the KR120R2700-2. When you double-click the robot in the eCatalog, it is immediately created in the simulation view. This central window represents your virtual production line or shop floor. After a short loading time, the robot model appears in the simulation environment. On the right-hand side of the screen, you can see the Properties panel of the robot, where all configuration and visualization settings are displayed. Because the robot was created by double-clicking in the eCatalog, it is placed at the origin of the simulation environment. This means that all position coordinates are currently set to 0. By scrolling with your mouse wheel, you can zoom in on the robot. To improve visibility, you can also resize the output window slightly to get a better view of the robot model. In the Robot Properties panel, you will find several tabs that allow you to configure different aspects of the robot. The first tab is the Default tab. Here, you can see and edit the robot name. You can also change the color of the robot to make it easier to distinguish from other components in the cell. In addition, you can switch the robot's visibility on or off, for example, to simplify the view while working on other elements. You can define whether the robot should appear in the bill of materials and adjust its name and description as they will be listed in the BOM. Below that, you can see the axis values of the robot. At the moment, the robot is in its default pose. Axis A1 is at 0 degrees, axis A2 is at -90 degrees, axis A3 is at 90 degrees, and axis A4 to A6 are all set to 0. Further down, you will find general robot settings. For example, you can define axis 6 as an endless axis, or enable the display of the robot workspace in a two-dimensional representation. In the two-dimensional mode, the workspace is shown as boundary lines around the robot. Alternatively, you can switch to a three-dimensional workspace visualization. In the three-dimensional view, the workspace is displayed as a semi-transparent volume, similar to a bubble surrounding the robot. Now that the three-dimensional workspace visualization is disabled again, you can switch to manipulation mode and select Interact. The Interact mode allows you to move and manipulate all elements in the simulation that are defined as movable. For example, if you click on one of the robot axes and start moving it sideways, the robot will follow this movement directly. If you select another axis, such as axis 3, and move it, the robot motion updates immediately and follows the axis movement. This interaction allows you to visually demonstrate the reachability of the robot axis, which is represented by the workspace lines. In this example, you can see that the robot wrist is following the workspace line exactly. When you move the axis in the opposite direction, the axis limits of the robot become clearly visible, and you can follow these limits precisely along the displayed lines. You can also rotate axis 1 to a specific angle and immediately see how the workspace lines and robot orientation update accordingly. At the same time, the axis values in the Properties panel are updated dynamically. If you want to define a specific value, for example setting axis 1 to -90 degrees, the robot will rotate to face a different direction. If you set it to +90 degrees, the robot will face towards you. To return the robot to its original position, you can simply click the reset button, and the robot will jump back to its default pose. In the Properties panel, you can also load energy supplies for the robot or remove them if they are no longer needed. In the same way, you can add accessories to the robot and delete them later if required. In the Action Configuration section, you can adjust signal-related actions that are used within the simulation. In the Option Package Configuration section, you can add different option packages provided by KUKA. For example, you can add the iiQWorks UI option package. This option is required later when you want to start a virtual robot controller and visualize the SmartPad. When you add the option package, a confirmation window appears, and you need to confirm this dialog to apply the change. Within the general settings, you will also find a controller components section. This area allows you to add additional controller-related components to the robot. These components provide extended controller functionality. You can explore and review them on your own, depending on your application needs. The next tab in the Properties panel is the Controller tab. In this tab, you configure the robot controller that will be used for the simulation. Here, you can assign a name to the controller and select the firmware version. The available firmware versions depend on what is installed on your local system. You can also configure network-related settings, such as controller addresses. If you already have a controller instance running in the background, you can select it here. This could be your local host or another controller that is available on the network. After selecting the target system, you can choose an instance name. If an instance already exists, it will be shown in the list and can be selected. For example, if you already have a Quantec controller instance available, you can simply select it here instead of creating a new one. Below that, you will find time synchronization settings. Some of these options may be disabled depending on the selected controller instance. If enabled, you can synchronize the controller time with sources such as KLI, KSB, or fast measurement inputs. For now, we will skip the time synchronization settings and continue with the next section. Next, we move to the RCS configuration. When running this robot in iiQWorks.Sim Basic, the Robot Controller Simulation, or RCS, is the only available controller type. This means the robot will currently be simulated using RCS. In the RCS settings, you can select different options, such as enabling specific simulation methods or viewing log output generated during the simulation. One important option is machine data generation. Enabling this allows the system to automatically generate machine data for the robot. If you already have pre-created machine data, you can disable automatic generation and load your existing data instead. In this case, we want the robot to generate its own machine data, so we keep this option enabled. When you click the play button, the system starts generating the real machine data for this robot within the RCS simulation. At this point, the robot is running in the simulation. However, you do not see any motion yet because no KRL program has been created yet. To continue cleanly, you can reset the program or reset the simulation before loading or creating a KUKA robot language program. We will cover this in a later video. If you open the KRL Executor, you can choose between different execution modes that define how the robot is controlled during simulation. You can completely deactivate execution so that the robot will not move at all. You can select local execution, which means the robot is simulated using the robot controller simulation. You can also select a virtual robot controller, which is only available in iiQWorks.Sim Advanced, or choose execution with a real robot controller, or a remote view connected to an external controller. Below these options, you will find additional settings that change depending on the selected execution mode. For example, if you select Remote View, only the previously configured connection settings are available. You could then connect to your local host or to a virtual robot controller if you are using iiQWorks.Sim Advanced. For this tutorial, we switch back to the local RCS execution mode. In the Signal Action section, you can configure different signal-related behaviors for the simulation. Here, you can enable features such as Release to Physics, which is also only available in iiQWorks.Sim Advanced. You can also enable and visualize detection volumes for specific tools, allowing you to see how sensing or safety-related areas behave in the simulation. These were the most important settings of the robot and its controller. Next, we add a second robot to the simulation. This time, we choose a small robot. For example, we select an Agilis robot. Here, we choose the Agilis Ultra variant. We drag and drop the robot into the simulation world. Wherever you release it, the robot will be created at that position. In this case, the robot is placed about 3 meters in front of the first robot. The coordinates are not exact yet, so we adjust them manually to position it exactly 3 meters in front. On the other side, we add another robot. This time, we choose a heavy payload robot, for example, a Fortec Ultra. We select a KR800 and drag and drop it behind the Quantec robot to clearly show the size differences between the robots. Now we have 3 robots in the simulation. However, in iiQWorks.Sim Basic, only one robot can be executed at a time. The system will notify you that running a simulation with multiple robots is not possible in this version. If you want to simulate several robots, you need to go to the KRL Executor and deactivate execution for the other robots. After disabling execution for 2 robots, you can start the simulation again. Only the program of the active robot, in this case the KR120, will be executed. If you are using iiQWorks.Sim Advanced, you can simulate and execute multiple robots at the same time, including operation with a virtual robot controller. Now let us take a look at some additional components available in the eCatalog. Inside the KUKA folder, you will find all components that are specific to KUKA but are not robots. For example, you can find different types of booster frames. In this case, we want to add a booster frame for the Quantec robot. We drag and drop the booster frame into the simulation environment and place it next to the Quantec robot. In the Properties panel, we can now define the specific height of the booster frame. For example, we set the booster frame height to 400 millimeters. When we switch to the pick-and-place manipulation mode, we can click on the robot and drag it toward the booster frame. As the robot gets closer, a green arrow appears, indicating that the objects can be connected. When the robot is close enough, it automatically snaps into position and locks onto the booster frame. This means the robot is now mechanically attached to the booster frame. If we move the booster frame back to the origin of the coordinate system, the robot moves with it. At this point, both components are connected and behave as one unit. Next, we add another component, this time a linear unit. We open the KUKA linear units and select the KL5000. We drag and drop the linear unit into the simulation environment. After initialization, we can configure the linear unit. First, we define which robot will be mounted on top of the linear unit. In this case, we select the Fortec robot. The robot machine data is updated automatically so the robot understands that it is mounted on a linear axis. We then drag the robot toward the linear unit until it snaps into place. You can see that the project analyzer automatically adapts the robot configuration. When we switch to interact mode, we can now move the robot along the linear unit. Any further modifications of the linear unit must be done in the linear track settings. For example, if we want to change the rated travel length of the linear unit, we do this here. We increase the travel length to 8,300 millimeters. After a short update, the linear unit becomes visibly longer. If we want to change the robot position or orientation, we also do this via the linear unit settings. For example, we rotate the linear unit by 45 degrees. We can also choose different energy supply positions, such as centered or side-mounted on the linear track. This concludes the overview of booster frames and linear tracks. We also have positioners that are currently supported in iiQWorks.Sim. You can drag and drop a positioner toward a robot. When it turns blue, it automatically connects, in this case to the Agilis robot. This means the Agilis now has 2 additional external axes that can be controlled directly by the robot. Later, when you go to the Program tab of the robot, you will see these 2 additional axes in the jogging interface, and you can move them together with the robot. The important point is that the interface between the robot and the positioner is defined in the Interfaces section of the settings. Let us go back to the Home view to take a closer look at more elements available in the eCatalog. Open the eCatalog, collapse the other folders, and navigate to the Miscellaneous category. Here you will find many components that help you build a complete cell layout. For example, you can add a belt conveyor. We drag and drop the conveyor into the simulation environment. Next, we add a conveyor sensor. You can snap it directly onto the conveyor and place it at a specific position. We then add another linear conveyor to the simulation. Using the pick-and-place manipulation mode, the conveyor snaps directly to another conveyor, allowing you to connect them precisely. This makes iiQWorks.Sim a very powerful tool, because you can quickly build up a clean and realistic layout. You can also add safety fences around the cell. Multiple fences can be connected to each other. You can also add a sliding door, which you can open and close interactively in the simulation. If you want to add object flow, you can use tools like the Conveyor Creator. However, in this example we are using iiQWorks.Sim Basic. When we press play, the system generates machine data for the Quantec robot, but no objects appear on the conveyor. To simulate object flow, iiQWorks.Sim Advanced is required. We now enable iiQWorks.Sim Advanced, including the modeling add-on and the connectivity add-on, to unlock the full functionality in File, Option, Add-on. Use the sliders to activate the available functionalities. After confirming, we start the simulation again. You can now see objects appearing and moving along the conveyor. In addition, we switch the KRL Executor for all robots to RCS mode. After pressing play, the entire simulation runs with robots, conveyors, and object flow. These were the first steps to quickly build up a complete layout in iiQWorks.Sim. I hope you enjoyed this introduction, and I look forward to seeing you in the next video.
Thank you for watching. We hope you find this video tutorial helpful. Don't forget to follow the KUKA channel for more updates and more exciting content. If you're looking for hands-on training, visit the KUKA College to enhance your skills. See you in the next video.
Making automation easier.